Kia ora, and welcome to a lesson on Level 2 networks. In this lesson, I'm going to look at how to draw a network based upon a given table, as well as using that draw network to find the shortest path from one node to another, the minimum spanning tree connecting all nodes together, and whether or not the diagram is traversable. This example is in an abstract form, which means that it is lacking context. And for the actual assessment, the context will be there, so your answers will need to include the given context to do with the connected nodes, whether they be locations and roads or points on a computer system and cables connecting those computers together, whatever the context may be. Okay, so we're going to start off by looking at how to draw the network. And you're going to want, once you've drawn your network for one of the sections, you're going to want to repeat that network for all the sections, assuming there's no change to the network. So the network we are drawing is given in this table, and we're going to draw it on the diagram below. Looking at the table, the way to draw it is to look at a column and a row. Okay, the number that is given in the table is in a column and a row, and that represents a connection between the column and the row. So this 13 here represents a connection between A and B. So on my diagram, I'm going to draw a line from A to B, and I'm going to give it the value of 13. So that could be 13 kilometers, it could be 13 minutes, it could be $13, depending on the scenario that I'm given. Here we've got no context, so it's just going to be the number 13. Once I've done that for A, I'm just going to cross it out so I don't do it again by accident. I'm then going to look at the next value in A's column, and that is connected to C, because it's in C's row, and it's value of 15. So I'm going to draw a line from A to C with a value of 15. So from A to C, value 15. So I've done every connection from A. Now I'm going to look at the remaining connections from B. So B has 3 connections in total because it's got this one here, plus it's got the 2 extra in its column. So in the column, we've got B, and it's in row D, so that means a connection from B to D of 5. So I've got a line from B to D, which is 5 long, and then I've got a line from B to E, which is 9 long. So on my diagram, I'm going to draw a line from B to E, and call it 9. Once I've got my B column done, I'm now moving on to my C column. So I've got CD 7, CE 19, CF 20. So CD 7, CE was 19, and CF was 20. So D, E, F. Now I'm in column D. D goes to F in 9. So I'm going to draw a line from D to F in 9. Don't worry about the fact that they're crossing over, just be careful where you're writing your numbers, because you want to know which number relates to which line. Is this 7 here related to this line or this line? Well, I've tried to draw it closer to this line just so that I know it's connected to this line and not this line, and the 19 is obviously close to this line here. Okay, so I've done DF, and lastly we're now going to draw the line from E to F, which is 7. So now I have drawn my diagram. There was 1, 2, 3, 4, 5, 6, 7, 8, 9 edges to draw. Have I drawn 9 edges? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, I have. And I've labelled up all of the edges based upon their weight. Okay, so now we're going to actually practice finding the other information. What is the shortest path? What's the minimum spanning tree? And is the diagram traversable or not? So we're going to start off with shortest path. And I'm going to use Dijkstra's algorithm to do this. If you don't know Dijkstra's algorithm, I have done a video using Dijkstra's algorithm to find the shortest path that you can go back and watch. And I'd recommend watching it before trying to do it here, because I'm just going to run through using it on this diagram. So Dijkstra's algorithm from A to F is the shortest path we're looking at. So we're going to be starting at A and finishing at F. Dijkstra's algorithm says go to your starting node and call it 0, put a box around it. From here, I'm going to look at all of the distances from A that I can go. So can I go A to B, which gives me 13. I can go A to C, which gives me 15. Okay, now I'm going to select the smallest of these two, which is 13, and I'm going to put a box around it. From B, I can either go to D, which adds 5 onto 13, which is 18. Or I can go from B to E, which adds 9 onto 13, which is 22. Okay, and I've gone to all the locations I can from B now. Looking at the diagram again, I'm going to choose the smallest of those three, which is 15 at C. And I'm going to look from C, where can I go? Well, from C, I could go to D. 15 adds 7, which is 22. 22 is not smaller than 18 though, so I'm not going to replace the 18 that is currently here, so I'm not going to write anything. From C to E, it adds 19 onto 15, which is 34. 34, again, is not smaller than 22, so I'm not going to replace the 22 at E with a 34. But from C to F, there's nothing written here, so I am going to write a number. 15 plus 20 is 35, so I'm going to write the 35 here. Okay, now I've looked at all the places I can go from C. I'm going to now look again at the remaining numbers, the 18, 22 and 35, and choose the smallest of those three, which is 18. Okay, from here, there's no point looking at B and C because they're already boxed, which means I've already found the shortest value to get to that location. So from D, I can actually only go to one other location, which is F, which is 7 onto 18, which is 25. Well, 25 is smaller than 35, so what I'm going to do is cross out the 35 and replace it with 25. So cross out 35, it is now 25, because you want the smallest value that can get there. Okay. So again, I've looked at every place that I can go to from D, so I'm going to look back at these numbers which are not boxed. Which of these is smallest? Well, 22, so I'm going to put a box around 22. I'm now at E, going to look at all the places I can go from E. There's no point looking at B and C because they're already boxed, and the smallest they can be. So E to F is 22 plus 7, which is 29. Is 29 smaller than 25? No, so the 25 is going to remain here, and that is the only place we can go. So we're now at F, which is 25. We put a box around it, and that is our end because we've boxed up our end location. Now we've found the shortest distance from A to F will be 25. We just need to work out which way we went to get there. So if you remember where you came from, that's great. If not, the way to do it is to look at this 25 and see if going backwards makes sense. So it's 25 minus 7, 22. No, it's not because it's 18, so they do not match up. 25 minus 20 is 5, so these two don't match up. But 25 minus 7 is 18, which do match up. So this must have been the edge I came along to get here. And then do the same thing now from D. Is 18 minus 7 15? No. 18 minus 5 is 13. So you must have come from this direction. And then from this point, well, 13 minus 9 does not go to 22. That's 13 plus 9. 13 minus 13 is 0, so this must have been the edge we came along. So our shortest path was A, B, D, F, which is equal to 25, whatever the units may be. So we would say the shortest path is ABDF, which is equal to 25. And then underneath, if you're wanting to go towards merit, you need to explain the method you used. So to find this, I used Dijkstra's algorithm, which looks at the cumulative distance from a starting node to every other node and always selects the shortest value of the smallest value. Okay, it's a very brief basic explanation of Dijkstra's algorithm, but it's using an algorithm towards a solution and being able to kind of state/explain that algorithm. Okay, so that's the shortest path. We're now going to look at the minimum spanning tree. So the minimum spanning tree is connecting all the nodes with the least total value of edges. So there's many ways of connecting all of the nodes together with the least number or least value of edges, such as this is an example. That's a way of connecting all of the nodes together. However, it might not be the minimum. So we're going to use Kruskal's algorithm. Again, there's a video on this if you don't know how to use it or do it. So Kruskal's algorithm says to always start with the smallest value in your network, which in this case is 5. And then you carry on selecting the smallest edge in your network without creating a loop. So after the 5, I'll note down which edges I've selected. So I've taken BD, which is equal to 5. Okay. So I've selected BD, which is 5. Next smallest edge in my diagram is either one of these 7s. Doesn't matter which one I select. So I'm just going to select either one. So I'm just going to select DC, which is 7, or CD, which is 7. Either way around. It doesn't actually have a direction, so you don't need to necessarily get the direction right, CD or DC. That's either one will be fine. The next smallest edge after 7 is the other 7, which is EF. Remember, you're looking to make sure you don't create a loop. So we need to be careful about creating loops. After the 7s, the next smallest value is 9. Either one of these 9s will work. However, selecting both 9s will not work, because if I selected both 9s, we're going to end up with a loop here. So it's just up to you which one you choose. It doesn't matter actually which one. So you can have multiple different ways of having a minimum spanning tree. You just need to state one of the ways of having a minimum spanning tree. So I'm going to select DF. Randomly, doesn't matter which one I select, but I'm going to choose DF. Okay, so DF equals 9. And on the other side, I'm just going to write down an edge that I'm not selecting, which is this BE, because it would create a loop. So BE has not been selected. Okay. After the 9, the next smallest edge on my diagram is the 13, which is connecting A and B together, and that does not create a loop. So I'm going to say AB is equal to 13. And because now all of my nodes are connected to the minimum spanning tree, i.e. they've got a line coming off of them selected, then I can stop. So my MST, my minimum spanning tree's total, is going to be 5 plus 7 plus 7 plus 9 plus 13, which is 41, I believe. And again, whatever units that may be, kilometers, dollars, minutes, whatever your diagram context is based upon, that would be this. And again, to get progresses towards merit, because this is kind of just like achieved, you need to then kind of state what method you use. So to find the MST, I use Kruskal's algorithm, where you select the shortest edge, and keep selecting the shortest edge or shortest edges without creating loops until all nodes are connected. So that's Kruskal's algorithm in a sentence. Very basic explanation of Kruskal's algorithm. Okay, so that's shortest path, that is minimum spanning tree. The last thing to look at is traversability. Okay, so is a network traversable or not? And this is, I think, the easiest, because all you have to do is count the number of edges coming from a node and state whether it is odd or even. So looking at A, there's an even number of edges because there's 2. Looking at B, there are 3 edges coming off, so it is odd. Looking at E, there's 3 edges coming off, so that is also odd. Looking at F, there are 3 edges coming off, so that is odd. Looking at C, there are 4 edges coming off, which is even. And looking at D, there are 3 edges coming off, so that is odd. And traversability says if no nodes are odd, if none of these were odd, and if they were all even, then the diagram would be fully traversable, meaning you could start anywhere and finish back where you started, going along every edge exactly once. If there are exactly 2 odd nodes, then the diagram would be semi-traversable, and you have to start at either one of the odd nodes so that you can travel along every edge exactly once without going along the same edge twice. However, if there's more than 2 odd nodes, as is the case here, we've got 4, then the diagram is not traversable. So this diagram here is not traversable because we've got more than 2 odd nodes, which means I cannot travel along every edge exactly once without having to go along the same edge twice to be able to complete the entire network. Okay? So again, this would be based on context, so you'd need to understand the context you were given. So it could be, can the person drive along every road in their city without going along the same road twice to have fun, or whatever the case may be. So without context, we're just going to say this network is not traversable, as there are more than 2 odd nodes, which means, and this is where you'd say it in context, so you can't travel along every road exactly once, but we're going to say it in abstract, which means you cannot travel around the diagram or around the network going along each edge only once. Okay? And that would be hitting the merit criteria, I believe, in this networks diagram. So but that automatically kind of hits achieve merit. Saying it's not traversable because there's more than 2 odd nodes, I believe, is achieved, and stating what that actually means in context is the merit part from memory. So that is up to merit for this networks assessment. There was a extra little bit in this question here, which is if a network is not traversable, remove an edge to make it traversable, and do this twice, removing the longest and shortest possible edge, and state the overall size of the network. That's getting you to understand that if you've got a network that's not traversable like we've got here, you can remove, if you wanted to, depending on the context, if you wanted to make it traversable, you can remove an edge from this diagram which would make it traversable, but only one edge. We're only going to look at one edge. So the way to do that is looking at the odd nodes, these 4, okay? You look at connections between odd nodes, okay? So there's multiple connections between odd nodes, okay? Got all of these are connections between odd nodes, and we're going to remove the largest one of these, which would create the smallest overall network, because if removing the largest value is going to make it a smallest value. And we're also going to remove the shortest one of these, which is going to make it the largest overall traversable network. Because when you, for instance, if I removed this 5 here, that's going to change this odd here to an even, because now there's only 2 edges coming off. So it's going to change this one in the middle to an even, which means now we've got exactly 2 odd nodes, which means that the diagram would be fully traversable from either one of those odd nodes finishing at the other semi-traversable network, for instance. So that was the extra part. That's kind of getting you to start thinking towards excellence of how can you manipulate a network for a given scenario. So if you wanted to make the largest overall traversable network, you'd remove the smallest edge between 2 odd nodes. If you wanted to make the smallest overall traversable network, you'd remove one of the larger edges, or the largest edge. In this case, there's 2 different edges I could remove to make it fully, 2 two edges I could remove to make it semi-traversable. So yes, so you look between odd nodes. That's basically the idea, is remove edges between odd nodes to sort of move yourself towards traversability. I could make this fully traversable by removing this edge here between these two and this edge here between these two, which would turn every node to even, and then it would be fully traversable. So that's another thing you could consider doing. Anyway, that's this example. Hopefully that has helped in some way towards your assessment. Good luck. I hope you do well, and bye.